Hello everyone. In this video we'll try to understand why wings are used and how they are so good at generating lift, and basically how wings work. You can find on YouTube and elsewhere on the internet common explanations of how wings work that sort of give part of the answer, but they're kind of missing a few important things. So we have the classic explanation of air flows faster on top and Bernoulli, and you have a lower pressure on the top surface causing, but this is kind of a kinematic, how lift is produced, and not really a why. It's not really a deep physical explanation. We also see the reason of pushing air down, deflecting air. We want a little more detail. And Cohen effect is another one of these kinematical how explanations. But a good understanding would allow us to answer two important questions. How does conservation of momentum apply? And why do we use wings? Why are they so great at producing lift? So first let's take a look at the conservation of momentum. So here we have upstream air momentum. Some momentum is transferred to the wing, and this transfer affects the air momentum after it has touched the wing downstream. So basically we can say that the upstream equals downstream, total downstream, or before equals after, right? Momentum is conserved. And so if we recognize in this momentum conservation that the magnitude of the upstream air momentum should equal the magnitude of the downstream air momentum, then we realize that we simply have a rotation of the upstream air momentum, and the reactions of lift and drag on the wing are simply the result of this turning. So let's call this deflection angle phi, and we can write some relations with the lift and drag ratio. And so here we have this angle here encompassed by this blue arrow as phi, and we can see that the lift is proportional to the sine of phi, and that the drag is proportional to 1 minus the cosine of phi, which is where 1 represents the upstream air momentum, and the trigonometric angles are relative to the downstream air. Well, the downstream air momentum is the hypotenuse in this case, and so we have lift being the sine of phi and drag being 1 minus cosine phi, which is the difference between the horizontal part of the downstream and the upstream. So here's our equations that we have so far. But we also recognize that even with no deflection, we know that we would still have drag due to friction. So we can add a small friction term. I mean, aside from mathematically, preventing us from having a 0 in the denominator, it's also a reasonable physical term. So let's compare this with experimental data. Okay, so on the left we have the lift over drag ratio as computed by this formula, with the friction term set to a small constant, a small arbitrary constant, and versus the deflection angle. And we can see it has this shape. We get better and better lift over drag ratio, and then we have some peak, and then it starts to go down. And we see this same pattern in experimental data. This is data I grabbed off of a NASA website, and we have the lift over drag versus the angle of attack. And the shapes are very similar, but note that the deflection angle and the angle of attack are not the same. They are not the same. So it's surprising that these curves are so similar. It could be that since these angles are so small that they could have been closely proportional, but there's no like reason that they should be the same. But anyways, here is obviously the stall point, and stall is when the wing fails to be a good deflector, and so that's where you get this huge deviation. But yeah, this is sort of evidence of the validity of this deflection interpretation of lift. And now we have come out with a with some reasons to explain why we use wings and why they're so efficient. It's really the trigonometry of it all. If you remember, maybe from high school math, that the so-called small angle approximations, where for small angles, the cosine of the angle is approximately just equal to 1, and the sine of an angle is approximately just equal to the angle in radians. So these approximations sort of, make sense in explaining why we can input a little drag and get out a lot of lift. This also provides a way to explain how unsteadiness might result in a lot more drag than steady flow, because a sinusoidal deflection of momentum would result in the lift components canceling out, and but the drag component still, averaging to a non-zero drag. So this situation would obviously not follow the lift to drag curve, and introduce additional drag as compared to the steady case. Well, thanks for listening. I hope you learned something interesting, and of course, if I said anything wrong, please point it out in the comments.